This is a review of the Norton and Thevenin transform methods. You first learned about these methods in Circuits 1, and what they are is an organized way to take a complicated circuit that looks like this into a much simpler circuit that looks like either a pure voltage source with a series resistor, and we'll call that voltage source VOC, and we'll call that resistor REQ for equivalent, or a pure current source. We'll call the current source ISC for I short circuit, and we'll again call that resistor REQ. And what we're saying is that if we were to take a black box, so this isn't a wire, this is the enclosure of a box, and box up our original circuit. So we only had access to the two output terminals. We could not tell the difference between any of these three different black boxes. And yet obviously from a circuit analysis standpoint, either the Thevenin here or the Norton is much easier to analyze. So the idea why they're useful is we can take a very complicated circuit, like in the upper left-hand corner, and break it into subsections, like the circuit that we've drawn the red box around, analyze that small subsection separately, find its Thevenin or Norton transform, plug it back in our larger circuit, and then complete the analysis. The reason why we call the resistor REQ is because it's the equivalent resistance seen between these two terminals, between the output terminals. And the reason why we call the voltage source VOC in Thevenin, or open circuit voltage, is that it is the voltage that we would measure if you actually connected a digital multimeter to this black box. In either the left or the right circuits, you would measure VOC because there's no current flowing, so there's no voltage dropped across the equivalent resistance. Similarly, we call the current source in the Norton equivalent ISC for I short circuit because if you were to short the output terminals and measured the current that flowed through that short, it would be equivalent to ISC. And perhaps it's clear that in the Norton equivalent, if you shorted this out, regardless of what that REQ would be, all the ISC current would flow through it, just like in the Thevenin equivalent, because there's no current flowing in the open circuit, all of the VOC would appear across the open circuit terminals. And this gives a hint about one of the methods that we can use experimentally to find the Thevenin or Norton transforms. There's actually 4 different methods that we can use to find them. And I'll cover each of those in a separate video. I'll next make a video on how to simplify sources using source transforms and resistor simplifications. And then last, I'll cover separate videos with examples of each of these methods 1 through 4 that we talked about in this video. So let's get started. There are 2 reasons why Norton and Thevenin transforms are useful. One is with academic style classroom problems. In this kind of problem, you've got a very complex circuit to analyze. In this circuit, say we're interested in the voltage across this resistor. We can break this complex circuit into 2 smaller parts. One, the Thevenin equivalent of everything contained in this green box, as seen by these 2 yellow circles, and the second, by everything contained in this blue box through the viewpoint of these other 2 yellow circles. You'll notice that each equivalent circuit only has 2 wires exiting, just like we drew up here. So each circuit can be represented, if we were drawing Thevenin equivalents, as a single voltage source with a single resistor. That would be the equivalent of everything in the green box. This is the equivalent of everything in the blue box. And now, the resulting circuit is much, much, much easier to analyze. The important thing to realize is that although all the interior voltages and currents in here in the equivalent circuit are lost, And the same thing for everything inside the blue box. The voltages and currents outside the box remain the same. So everything in this area here, all those voltages and currents in the unchanged circuit have remained the same, and the voltage you were asked to find originally, it's remained the same. The second reason why Norton and Thevenin transforms are useful come from the need of practicing engineers who put together circuits made from sub-circuits that are perhaps designed by others. Here's an example of a sensor circuit. It's a fairly complicated circuit because it requires the sensors to be biased. You measure the voltage output of this circuit fragment, and you find it's 10 volts when there's light, and it's 0 volts when it's dark. You want to drive this LED that requires 2.2 volts at 20 milliamps. And the question is, will that sensor circuit give a sufficient drive to operate the LED? At first blush, it seems like it might give too much voltage, and you'd need to cut that voltage down by a resistor, and if so, what resistor value would you use? To answer that question, you'll first find the Thevenin equivalent of that circuit. And the Thevenin equivalent of that circuit might look like this. And now to it, you connect your LED. And now it should be obvious that there is no way that this circuit can provide the LED requirements. It's not that it provides too much. It actually doesn't provide enough. If that LED drops 2.2 volts, then that only leaves a total of 10 minus 2.2 volts, or 7.8 volts across the resistor. So how much current will flow through your LED? It's only going to be 7.8 volts divided by the 1 kilo ohm resistance it sees, which is only 7.8 milliamps, which is not enough to drive the 20 milliamps that the LED needs. So the circuit isn't going to work at all. This kind of insight can only be seen by looking at the Thevenin equivalents. If you just simply looked at what the output of your sensor circuit was, found it was 10 volts when it was lit, and 0 volts when it's dark, you might come to the erroneous conclusion that it actually provides more than enough voltage for your LED instead of not enough.